welcome everyone in this week Quantum Information and Quantum Computing seminar. We have a pleasure to host Błażej Ruba from Chair of Mathematical Methods of Physics in University of Warsaw. So Błażej is a mathematical physicist working on many body physics, algebraic techniques, a bit quantum field theories, with some interest in quantum information as well. And today we'll be thinking us about his work. Did you do this work when you were in Copenhagen still?
Yes.
Because Błażej spent some time in QMath in Copenhagen, and he'll be telling us, about asymptotic, applications of like asymptotic analysis of representation theory to quantum channels. It's great to have you, Błażej. The floor is yours.
Thank you for the introduction and for the invitation. And yes, I will introduce a little bit semi-classical methods in representations, mostly of unitary groups, which I mean, quite possibly is already familiar to some of the audience, but then I will move on to quantum channels, which are invariant under quantum channels between states on irreducible representations and invariant action of the group. And I want to say that this will be loosely based on work with Tomasz Laskieri and Jan-Filip Soloway, but most of what I say is actually sort of introductory, so only a small part of it will be my results. So this is the outline. I will introduce a little bit the semi-classical methods in large representations of groups, where the semi-classical parameters essentially is the inverse of some measure of the size of the representation, and a good example to keep in mind is unitary or special unitary groups acting on large symmetric representations. Then you can think of systems of symmetric states for n qubits, if you like, and then one over n would be the semi-classical parameter. I will then present some applications to equivariant channels in irreducible representations, and maybe link a little bit to the Wehrl conjecture about minimal entropy. So let's start from coherent states. The setup is following. We start with a compact connected D group, and again, you may as well keep in mind the example of special unitary group of some dimension for the rest of the talk. And we consider some irreducible representation with a highest weight vector, here denoted by little h. Then there is a famous resolution of identity on the representation given by an integral over the group. So we take the rank 1 projection onto the coherent state, onto the highest weight vector, and rotate it with the group action. This gives a resolution identity basically by Schur's lemma. Now this integral over the group is sort of redundant because there is some subgroup here denoted K, which preserves the highest weight vector up to phase factors. So this integrand here is in fact invariant under multiplication of the group element J by something from the subgroup from the right. So we can write this integral as the integral over the quotient space G mod K. So this G mod K is the right sort of parameter space for these states that we integrate over, and we can of this expression as these projections multiplied by the dimension provide us these are positive operators, and they define a positive operator valued measure parameterized by points of this G mod K. Now I would like to give you a little bit of idea what this space G mod K may look like. So the simplest example is the situation that appears for representations of SU2. Then we have representations parameterized by the spin parameter, and for all these representations, maybe except for the trivial zero-dimensional, the highest weight vector, that's the top spin vector, is invariant under a subgroup of rotations around the third axis, so invariant up to phase factors. And the space G mod K is the two-dimensional sphere, essentially the block sphere. We can think of spin J representation as a symmetric tensor product of 2J two-dimensional representations, so symmetric state of 2J qubits, if you like. And this sphere you can think of as the block sphere. The semi-classical regime is the situation where this parameter labeling representations goes to infinity. We can think of the space of functions on the sphere, for now in some loose sense, as the limit of matrix algebras of these spin J representations. Maybe at first, let's just take a quick look at what are the irreducible representations occurring, say, in the space L2 of the sphere. That's famous spherical harmonics labeled by integers L from 0 to infinity. If we look at the matrix algebra of Hj, then irrespective of whether Hj itself is a half integer or integer spin, the matrix algebra will only contain integer spin representations, but truncated to 2J. The maximal spin in the composition of the matrix algebra of Hj is 2J, which goes to infinity as J goes to infinity. So all the representations that you see on the L2 of the sphere appear eventually for large enough J, and the sort of multiplicity with multiplicity 1 on both sides. All right. Maybe let's say something more general. So general features of these spaces, G mod K, these classical phase spaces, let's say. So here I define G mod K, essentially as the orbit of the highest weight vector in the projective space of the representation. Equivalently, it may be described as the so-called co-adjoint orbit. So this is the orbit of the highest weight of the representation in the dual of the Lie algebra. This is related to a famous program of realizing irreducible representations of the algebras by some sort of quantization of co-adjoint orbits. So the geometric structure of this space is quite rich. It's a so-called Kähler manifold, meaning that it has a complex structure. It's a Riemannian manifold, so the corresponding to a notion of distance. And there is a symplectic structure which allows to define Poisson brackets of functions. One should be able to in class.
Sorry, so can I just check the definition of what is the definition of the highest weight vector in the irreducible representation space? It can be any vector or
no. For compact, right? So maybe let's start from this example of SU2. So maybe you are familiar with the ripple of operator J minus, J3, J plus in the Lie algebra of SU2, and a very standard thing is that we diagonalize this one element, and this J minus and J plus, they increase or lower and increase the eigenvalue of J3. So the highest weight vector is the one which is annihilated by J plus, and it's also the eigenvector of J3 to the largest possible eigenvalue. in the given representation.
Mm-hmm.
And this generalizes to other compact groups where the algebra can be split into sort of three parts, where there is a part that you diagonalize, commonly called cartons of algebra, and there are some raising and lowering operators. So, for instance, if you think about the unitary group, the thing that you diagonalize is in representations. These are diagonal matrices, and raising and lowering operators are given by upper and lower triangular matrices.
But so far, you do not use any kind of structure that it is the highest weighted vector. Any kind of non-zero vector would give same property, like
Any vector in the representation would give a resolution of identity like that, but taking the highest weight vector gives, in some sense, the best resolutions of identity. For instance, the geometric properties of this, what I call phase space, G mod K, are the nicest if you start from the highest weight vector.
I see.
So, for example, the fact that it's a complex manifold and that it has this symplectic structure that's related to this particularly nice properties of the highest weight vector. So these these orbits of highest weight vectors are very distinguished in many different ways, and also in computations, you can compute much more, and
But in a system, maybe like the least quantum ones, right? Those.
That's in a sense true. Very often these highest weight vectors are product vectors, which we'll actually see in the next slide. Thank you. Okay, any more comments? I wanted to make this comment also. I mean, if it sounds unfamiliar, just ignore it. It will not be important for the rest of the talk. But the representation itself can be constructed in terms of the space G mod K. So there is sort of the opposite approach where we start from these spaces and we sort of quantize them in a suitable sense, and we construct all representations of groups. And this for semi-simple for compact groups, this has been worked out in the 50s by Wehrl and Weih.
Can I ask, like, what if you have some other homogeneous space, like other elements, do you think like we cover all the space of representations then?
Yes. So actually, maybe it's a good idea to go to the next slide, because there will be an example of these spaces, and I will comment maybe a bit on your question. So this is an example of the group SUD, and now let's take D to be 3 or higher. There is a way to parameterize reducible representations of the group by the so-called Dynkin indices, which are natural numbers. There is D minus 1 of them, and so that these tuples of Dynkin indices are in one-to-one correspondence with the classes of irreducible representations. And here there is a formula for the highest weight vector of the representation with the given Dynkin indices as a big tensor. And here these little EIs are basis vectors in the fundamental representation of SUD. So this is so wedges are the skew symmetric tensor products. So for each k from 1 to D minus 1, we take the k-fold wedge product of the first k vectors. We raise this to the power nk. So this is a symmetric tensor power, right? Because a tensor product of one vector is a symmetric tensor. And then we also tensor over all these k's, and this gives highest weight vectors of all the representations. So in general, elements of representations look quite complicated if you want formulas for say projections onto irreducibles. These are quite complicated, but highest weight vectors can be written down explicitly and product vectors. And what are these phase spaces corresponding to these representations? Well, the simplest case is if only one Lincoln index and k is non-zero, then this phase space is the Grassmannian. This is the manifold of k-dimensional linear subspaces in CD. And of all these manifolds, the simplest one is the manifold of one-dimensional subspaces, which is the complex projective space. Or d minus one-dimensional subspace is basically the same because we can take orthogonal complements. So this complex projective space is the closest analog for the sphere from the case of the SU2 group, and it's relevant. This complex projective space is relevant for the symmetric representations of SUD, and let me maybe say that I will have many examples which are about the group SU2, sort of for simplicity of notation to make it more digestible. But almost everything that you can do for SU2 generalizes to the case of the complex projective space. Whereas if you encounter more complicated phase spaces, the analysis gets harder. And there is still quite a lot that is done and known about these Grassmannian manifolds, which are sort of the next in hierarchy of complication. But this is still the very special situation where only one Dynkin index is non-zero. So this is extremely special. So here, sort of the opposite end of the spectrum, so to say, is the generic case, namely when all the Dynkin indices is non-zero. And this corresponds to the situation where the highest weight vector has the least possible amount of symmetry. The highest weight vector is always well, an eigenvector of the diagonal subgroup. This is the minimal stabilizer of the highest weight vector. And if this stabilizer subgroup is small, then G mod K is a sort of large manifold, and it's a really complicated space. One thing that is very complicated about it is, for instance, that the L2 of the phase space decomposed into irreducible representations has large multiplicities. Whereas for Grassmannians, there are no multiplicities at all. So they are much easier to work with. All right, so I was supposed to go back to your question. So if you start from this maximal phase space, G mod K, where K is the this diagonal subgroup, so the so-called maximal torus of the group, then quantizing this, you can recover all representations. And this Wehrl theorem tells a story about exactly how you can get all representations. Now, if you have special representations which have some additional symmetry, then you can obtain them by quantization of much simpler spaces. All right. So here in this slide, I introduce quantization and dequantization maps. So what do I mean by that? This will be some. So first of all, op is a map which takes a function on the classical phase space and produces an operator on the representation. And the way it produces the operator is we take this POVM introduced earlier by rotating the highest weight vector around, and we introduce a function, the function as a weight in this integral. And so, for instance, the fact that we have a POVM, so the projectors integrate to identity, corresponds to the statement that op of the constant function equal to 1 is the identity operator. And there is a map in the opposite direction where we take an operator and multiply by the projection, take a trace. So if this operator T is say state, a density matrix, then you can interpret this formula as the expectation value of the operator in coherent states. And these are two nice maps, classical to quantum and quantum to classical, which are positive, so they preserve positivity. And if you want an operational interpretation, you could think of them as preparation and measurement procedures described by a POVM.
So is this the quantization like left inverse of this quantization?
They are not inverse to each other. They are in some in a way that will be explained next. They are approximately inverse to each other only. And well, the semi-classical analysis aims to understand how properties of operators, like spectral properties of operators, correspond to properties of functions. I will say just a little bit about it. So, okay.
So I guess they are not inverse because the operators P of omega are not so right?
Yes, that's exactly right. So, so a very important object in this theory is the so-called Berezin transformation. In honor of Felix Berezin, I believe. So this map, this is an operator on the space of functions on the phase space, which is the composition. We first quantize and then dequantize. This dequantization, usually called Cauchy map. You can just take the two formulas from the previous slide, plug one into the other to get the formula for the composition. The lag. I need to be more patient. If you look at this formula, this is an operator which has an explicit integral kernel given by dimension of the representation times trace of the product of projections. This trace is equal to 1 when the states are at the same points of the phase space, and there is a big normalization factor, dimension of. What did I do? Maybe it's better if I just use my if I change slides here. This integral kernel integrated over the whole phase space gives 1. So it's a sharply, if you take a large representation, this is a sharply integral kernel, and it acts as approximate identity. Right, this integral kernel is approximately a delta function, and that happens if the representation is large, and maybe we need a little bit of regularity of the function f, maybe continuity or something like that. And if the Berezin transform of the function f is close to the function f, then the spectrum of the quantization of f reflects the function well. And oh, thank you. So here I wrote just an example set of inequalities for trace of the p power of the absolute value of the operator. So essentially, sum of singular values to the p power. And this can be upper bounded by a corresponding integral on the sphere, just of the function f itself, and lower bounded by the same thing, but with a transformed function. So you see, if f and b of f are close, then and this thing in the middle is sandwiched in between them, then you see that it's very well approximated. On the other hand, if b of f is far from f, then there is a lot of room between these two. These are still true inequalities, but they may be useless if these two things are far apart. You can think of this Berezin transformation as some sort of quantum blurring that occurs because, well, there are no perfect measurements in quantum theory. If you prepare a state and then measure, then you'll get back the same thing. Anyhow, this here is for these particular norms of operators. There are similar inequalities for entropy functions or maybe for traces like this one. So this can be used in the semi-classical analysis of partition functions in quantum statistical models. And this is joint usually called Berezin-Lieb inequalities. Mostly discovered already by Berezin, but Lieb popularized this by using these techniques to actually analyze some non-trivial quantum statistical models of these inequalities for the exponential function. All right, so here is an example how this Berezin transformation looks like for SU2. So we take the spin J representation, and I mean, recall the Berezin transform so far denoted by B, but it depends on the representation that we are studying. So now it will have an index J. The J Berezin transform of F is given like this, and you see here in this parenthesis, omega and omega prime are just points on the sphere in 3 dimensions, and this object in the parenthesis is just a trigonometric function basically, but it's maximal when omega is equal to omega prime, and so for coincident points, and it's raised to a very high power. So essentially this function behaves like a Gaussian, localizing on a length scale of order J to -1/2. So this gives you some idea how the sort of the range of the blurring of the quantum blurring is given directly by the index of the representation. And so this is an explicit formula as an integral kernel. The spectrum of this operation is also completely explicit. So here is the resolution of identity of this operator. So written in terms of this is an invariant operator on the sphere, so it can be written as a weighted sum of projections onto the, well, pi L is the projection onto the order L spherical harmonics, and the coefficients are explicit. They are some ratios of factorial. Doesn't matter what they are exactly, but each of these coefficients, if you fix L, then each of these coefficients converges to 1 as J goes to identity. But what's maybe not so obvious from the original integral formula, but is apparent here, is that, this, even though this looks like Gaussian smearing, it has a hard cutoff in terms of, the spectral resolution. It only goes to representation up to 2J. And this is clear that this should be the case, that all higher representations are annihilated, because all the maps that we are considering are invariant under the action of the group. So they sort of preserve the index of the representation, and representations higher than 2J do not occur in the matrix algebra of the representation Hj. So all these higher representations are sort of annihilated by the quantization map, and this is reflected by this formula. And here, the third formula here gives you an asymptotic expansion of this Berezin transform operator, and there is a more or less explicit full series in powers of 1 over J, like this, with higher and higher order differential operators.
So what is omega here? Sorry.
So omega is the point on the sphere. So in the previous transparencies, I used omega as a generic symbol for a point of this classical phase space. But here I specialize to the case of the sphere. So you can literally think of two-dimensional sphere in R3, and omega is a unit vector. This formula here involves the scalar product of unit vectors.
Yeah. And always true that the spectral gap of Bj is related to the spectral gap of the Laplacian on the space, or?
Well, so in the case of S sphere, and also in the case of complex projective spaces, the Berezin transformation can be written as a function of the Laplacian in the spectral theoretic sense. So, and this formula here essentially tells you which function. So the Berezin can be written, the function is some ratio of gamma functions essentially. There is a funny ratio of gamma functions such that if you plug in the Laplacian of the sphere into it, you get the Berezin transformation. So this also happens on the projective space. The formula is almost the same as here. There are some dimensional shifts, but almost the same formula. Now for more complicated phase spaces, the algebra of invariant operators on the phase space may be much richer. And for instance, on the Grassmannian of k-dimensional subspaces, where k is at most half of D, the algebra of invariant operators has k generators. So there is sort of k invariant Laplacians, but they all commute, and still there are formulas which allow to represent Berezin transformation as a function of k commuting, say, generalized Laplacians. These formulas are much harder to derive than this one, but nevertheless, these formulas exist. If you consider an even more complicated phase space where multiplicities of representations occurring in L2 are non-trivial, so representations occur with higher multiplicities, then the algebra of invariant operators is non-commutative. And there are no known formulas for expressions of Berezin transforms as functions of differential operators. It would be have some sort of non-commuting functions, and the spectra of Berezin transforms are not known in general. So there are statements that the fact that it converges to identity operator in some limit is quite general, but I think the question of optimal rate of convergence and error bounds, and so essentially the spectral gaps that you're asking is largely open, I think.
So like in general, those Berezin transforms, there will be like equivariant with respect to group action. So
the quantization map is equivariant with respect to the group action, because there is a phase space, which is a homogeneous space for the group, and we map to a space which also is acted on by the group. Everything inside is equivariant. Berezin is composition of two equivariant maps. And so maybe a word on products of quantized functions. So the gold standard is that there is something called star product, which is an asymptotic series given by some differential operators that allows to approximate the product of two operators. So it's not just the product of functions, because, well, product of operators is non-commutative. And in full generality, this star product is quite complicated, inexplicit, given by some diagrammatic expansions. There are only some special cases where this is explicit and very sort of like completely understood, I would say. So for instance, for SU2, or maybe for projective spaces in general, well, here I wrote for you the first two terms of the expansion. You see that if you took the commutator, there are terms, so Fg, product Fg, and product of gradients of F and G. These are expressions which are symmetric in F and G. So if you take the commutator of these two, you would recover the Poisson bracket as the leading order term, and 1 over 2j plus 1 would play the role of the H bar. And there are rather explicit formulas for the full expansion. Higher order terms have more powers of 1 over j, and they have higher order differential operators. And also, maybe my small contribution to this is now for projective spaces, we have very strong bounds on remainders of such series truncated to a finite order. So in general, it really doesn't matter if this series, like full series, converge. That's an irrelevant question. What's relevant is you want to truncate and estimate the remainder. And you want to know when truncated expansions give you a good approximation. And here the error of the truncated expansion can always be, in a suitable sense, bounded exactly by the next term of the expansion. You don't need to sum all of the subsequent terms. Exactly just the one next term of the expansion bounds the whole error. And this may be counterintuitive, why it's enough to bound one term. But essentially, there is a mechanism which works roughly like that. These are sort of alternating series, and the error. So at each order of the expansion, the approximation overshoots in one direction, and the next correction has sort of opposite sign and tries to correct for the previous error, but overshoots. So it's an alternating series like that, and there are basically, I mean, it's clear that you can never do a better bound than the next term of the expansion, right? So here, so far, I talked about the setting where basically I treated the function as fixed and considered quantization of the function in higher and higher representations. In fact, this is not really the practical point of view, because the function that you consider may be, for instance, the Cauchy function of some operator in a large representation. So the function itself may be J-dependent, essentially. And that's why this quantitative error bounds with optimal regularity assumptions on the functions are important. So say if you consider a function which is the Cauchy function of some operator, then taking each derivative essentially costs you some power of j. I mean, in your remainder bounds. So if you want optimal bounds, you also need optimal regularity assumptions, not using too many derivatives. For instance, here, I told you that the next term that the error of the expansion is always controlled by the next term. So say you wanted to approximate it op f times op g by op of the product of functions. The next term of the expansion is of order 1 over j, and it has first derivatives of f and g. So essentially you can bound the whole error of the expansion translated like that by 1 over j times some norm of the first derivatives of the functions f and g. Now, what if you want to approximate operators? Say you have an operator on a large representation, and for instance, you ask whether it's close to the quantization of its Cauchy function. Then the role of derivatives is replaced by commutators, say with the algebra generators. And here is just a small example of an inequality which states this. So suppose that you have an operator rho on Aj, could be a density matrix or something, and we compare it with the quantization of its Cauchy. And the right-hand side has a factor of 1 over 2j plus 1, and there is a norm of the Casimir of the group acting by commutators, acting on operators by commutators. And so here Ji are the standard spin operators, and this norm is some more, some norm. Anyhow, I want to point your attention to the fact that if you take a general rho, then in the worst case scenario, each commutator with a spin operator could contribute a factor of j. So this expression could be of order j squared, and this inequality may very well be completely useless. So it's not true that any, and one should not expect that any operator is well approximated by the quantization of the Cauchy function. I mean, we are going to the classical world and back to quantum, and that introduces some sort of blurring, and for very quantum object, it's not faithful. But anyhow, you know exactly what you need to check, what term you need to bound in order to know.
So, Błażej, can I ask, like, just maybe on conceptual side? So, like, I mean, okay, it's actually very nice technically, but like, I'm just like, also, like, how should I think about this Berezin transform? Is it like, is it useful to, because even from our work, I can imagine many scenarios where there are some operators that whose properties I don't really understand, and like, would it is it like easy computationally to maybe take some operator and compute its Bayesian transform? Like, just it's maybe easy to operate with it? I don't know.
Well, it's certainly a useful technical tool. So I mentioned this. So I want to get to the. I mean, getting ahead of myself a little bit, but I want to get to the asymptotics of quantum channels, and we derived some formulas for asymptotics of quantum channels between large representations and obtained formulas for the entropy of the output entropy of channels, and this somehow in the process of the derivation you verify that your operators are quantizations of symbols which are, I mean, sort of in this good semi-classical regime, namely the function is close to its Bayesian transform.
So this Bayesian transform I can like morally regard as like some semi-classical approximation to quantum objects.
Yeah, and it gives you sort of a criterion for the semi-classical behavior, and I mean, there is also the sort of Bayesian acting on operators, namely exactly this object. Take the Fushimi and quantize back. This is sort of the Bayesian transform acting on operators, and here exactly we ask whether rho is close to the Bayesian, and I'm showing you an example where you can decide whether it's close by just computing with the Casimir. So you don't need to actually compute the Bayesian, which will be more complicated. But still, it is not true that for any operator the right-hand side is small, right? I wanted to emphasize this caveat that there is a formally small parameter, but the right-hand side will still be large. So it depends on the operator that you are studying, and that's why these sort of optimal remainder bounds are important in this business, because you need to be able to decide whether the remainder is actually small or not, and it's not always small, especially if you are in some very quantum regime.
I have another stupid question. Is this map like the takes an operator to its Fushimi and then quantizes again? Is it a quantum channel?
Yes,
It's completely positive.
it's completely positive.
So
it's actually an entanglement breaking channel also.
Oh yeah, okay, sure.
And this will even come. But yeah, it's a quantum channel. It's a quantum channel of the form measure and then prepare back.
Oh yeah, okay. From this view, oh, yeah, sure.
Okay, so let me relate this to quantum. First talk a little bit about quantum channels. So I will talk about quantum channels between irreducible representations and invariant under a group action. And there is suppose we have a map phi, which goes from operators on one space to another, and we want to know whether it's completely positive. There is this beautiful criterion due to Chai and Gieniokowski, which tells us to compute the so-called Choi matrix and check whether it's positive. And the Choi matrix we can regard as an operator on the tensor product of the representations, K times the dual space of H. And this is the completely positive part. We would also like maps which are trace preserving, but trace preserving is just a normalization in the case of equivariant channels. Like everything is trace preserving up to an overall rescaling. So in the end, there is a correspondence one-to-one between equivariant channels and positive operators on this tensor product representation, which are invariant under the group action and have a specified trace. That's a normalization factor. And quantum channels form a convex set. And whenever you have a convex set, it's interesting to know what are the extreme points. So for instance, if you have a triangle The vertices of the triangle are the extreme points, and in general, extreme points are points which do not lie on any line segment inside the set. And by this characterization of equivariant channels in terms of Choi and Miłkowski, the extreme points of the set of equivariant channels correspond exactly to Choi matrices, which are up to a normalization factor projections onto some irreducible subrepresentation in this tensor product. What does this tell us about this set? Well, it depends a lot on what does the decomposition of this tensor product into irreducibles look like. Namely, if it's multiplicity free, then for every irreducible representation in the tensor product, there is a unique projection onto that irreducible. Whereas if you have something with multiplicities, you may have some representation, tensor, some multiplicity space, and you can take a projection onto this representation times anything. So anyhow, I mean, you need to somehow resolve the multiplicity, and there is infinitely many ways to choose an irreducible subrepresentation with a given representation type. Whereas for multiplicity-free decompositions, there is only one projection for each irrep that occurs in the decomposition. So in the multiplicity-free case, there are finitely many extreme points in this set, and therefore channels form a simplex. And this multiplicity-free condition is always satisfied in the SU2 case, but not general. For larger groups, I mean, the generic situation is that you have multiplicities, actually. So it's a rather special in highly symmetric cases.
So by this picture, I feel like so any POVM equivariant CPTP maps can be decomposed as just a sum of extreme CPTP, and in turn it means that any by a Choi Miłkowski isomorphism, it looks like any C phi may be decomposed as the sum of irreducible representation projection. Is this correct?
Yes. So I mean, in general, if you have a convex set, then any closed, say, compact convex set, like here, any point in the set can be written as a convex combination of its extreme points. But simplices, so sort of higher dimensional analogs of triangles, are even particularly simple convex set. They are the simplest convex sets in existence, because every point inside the simplex can be decomposed, can be written as a convex combination of extreme points, so vertices of the triangle, in a unique way. So there are unique so-called barycentric coordinates. So yes, in this multiplicity-free case, there is a finite number of extreme channels, and every equivariant channel is a convex combination of elements of this finite family. So the study largely reduces to the understanding of this finite family of channels. So this is the case of SU2. We all know how representations of SU2 decompose under tensor products. So, and I wrote explicit formulas for the channels. So channels from J to K are extreme channels. I mean, extreme channels are labeled by an additional parameter M, where M is from this something between K minus J absolute value and K plus J. And there is some explicit formula involving projections onto irreducible and partial traces, and maybe details of this formula are not so important, but I wanted to illustrate that these are explicit objects which have some formula and so on. And I wanted to give you some special cases and interpretations of these, some specific channels in this simplex. So again, we are looking at maps from J to K, and there is the channels form a simplex, and the vertices are labeled by this M. and M is in some range, starting from the difference of J and K and ending at the sum. And one very distinguished value of M is the minimal M, which is J minus K if the J is the larger one, and K minus J if K is the larger one. And these channels are some very explicit objects. In the case of channels going down, so reducing the spin, this channel is just the partial trace. And in the case of channels going up, this channel is what I believe in quantum info literature called an optimal cloning channel. If you, I think I will not explain this because probably most of the audience knows this more than I do, but the maximal is also very distinguished. The maximal value of M is related to the so-called universal NOT gate. So suppose you have some number of qubits, which are all in a pure state represented in some represented by some point of the Bloch sphere, and you would like to map them to an all to orthogonal state corresponding to the opposite point of the Bloch sphere. That is not possible to be to do perfectly, cannot be realized by a quantum channel, but it can be approximately realized, and I believe this maximal channel somehow is the best approximation of this operation. And this maximal channel, unfortunately, I didn't write the formula here, but it can be given in terms of a measure and prepare form. So it's an entanglement breaking channel. One remark, so there is an important operation which on the quantum world is the transposition with respect to an invariant bilinear form on the representations. In the classical world, it corresponds to the inversion on the sphere, antipodal map on the sphere. And the quantum implementation of this thing is a positive map, which is not completely positive. And the one nice property of entanglement breaking channels is that if you compose an entanglement breaking with a positive map, you still get something completely positive. And if we take this maximal channel composed with the transpose map, we get something which is exactly this composition. First take Hushimi in representation J and then quantize back in a different representation, and that you can regard as a measured prepare protocol of cloning. This is a CPTP map, but it's not one of the extreme points of the simplex. And I should really wrap up, but let me just state this. So convergence of channels to measure prepare forms. So we consider the following setting. We consider channels going from representation J to K. And let me, for simplicity, fix J and take K to infinity. First of all, in reality, J could also grow, but the point is that there is a hierarchy. K is much larger than K, and I wanted to simplify statements, so let's just fix J. K goes to infinity. Second remark is that there is a dual statement where the input representation is growing, and the output is fixed. So that's, basically trivially follows from this one. Anyhow, so the channels, the extreme channels, correspond to a choice of the upper index, and very unfortunately there is a typo, but I cannot write on the display right. So this J here should be K, but doesn't matter. So this so there is a little m parameter here. It's not the original capital M because it's just shifted by this K here, but when little m goes from minus J to J, this set of channels goes through all the extreme points. And this is approximately given by some ratio of dimension and then measurement, but not this Hushimi function measurement, because there is an index m here. There is some other measurement with some other POVM, which depends on the little m, and then quantize back. There is a relative order of order 1 over k. By relative, I mean that it's 1 over k in comparison to the size of the terms themselves. And
So this other measurements, is it just smearing of the like a coherent states when you start from weight M state?
Yeah, so exactly.
Okay.
So this I tried to convey here. So this HJM is like the Fushimi function, but here the projection is the projection onto the spin M state, but in the direction given by the point omega on the sphere, right? So projection onto the eigenspace of J in the direction omega onto eigenvalue M. And the nice thing is that these particular POVMs indexed by M are exactly the extreme points of the set of POVMs on the sphere. So this result gives also some nice one-to-one correspondence asymptotically between the set of channels and the set of POVMs. Both sets are simplices and they have their vertices are naturally matched to each other in the limit. And okay, I didn't explain in detail, but one of the main things that these semi-classical tools allow to compute is traces of functions of operators approximately. So trace of a function f of g is approximately the trace of the composition. Now our channel outputs are approximated by quantizations of some modified Fushimi functions. So this defines what is the g that we want. And let's take f to be the function relevant for the von Neumann entropy minus T log T. Then this is the formula that we get out of the calculation, the semi-classical calculation. There is the von Neumann entropy of the output of the channel acting on tangentity matrix ρ has a term which is independent of the density matrix, logarithm of the ratio of dimensions. And then the leading correction to this is like an integral of P log P, where this classical probability density P is given by the outcome of this generalized measurement corresponding to the channel.
What's the integration variable here?
Yeah, this is the integral over omega. So this Fushimi function, this modified Fushimi is a function of the sphere, and I didn't write it the omega. Sorry. So the first term is of order log k. This term depends on j, but it doesn't depend on the size of the output representation. So this term is much smaller, and the corrections are shown to be of order log k divided by k. If you computed more general functions, you would expect the next correction to be of order 1 over k. But because this function relevant for von Neumann entropy is not differentiable at 0, you get this logarithmic factor. So yeah, so these are output entropies, and maybe very briefly about the Wehrl leak problem. So Wehrl entropy is the entropy, this minus P log P for the Fushimi function of a state. And it's very unfortunate that I called the density ρ, because ρ used to denote the density matrix. And here I think I called density on the phase space ρ. And this was originally proposed for bosonic degrees of freedom, which also have their own coherent states. And Wehrl conjectured that this Wehrl entropy is minimal when the state that we take is also the coherent state. So the Wehrl entropy is defined using the coherent states because you take the Fushimi function. The conjecture was that it's minimal for coherent states. And it took a long time, but eventually Elliott-Leib proved this, and then asked the same question for coherent states in the setting of compact groups, including SU2. And some number of years later, he himself, with his student, so Solovey, proved this first for SU2 and then for symmetric representations of SUD. And this is solved also for some non-compact groups, but generally speaking, it's still open for more complicated representations.
Or SUD also, so.
Yeah, so it's only solved for its very specific representations, namely the symmetric representations. So here, to relate to the result, I showed you the minimal output entropies for channels involve this modified Cauchy functions, which are defined in terms of weight states, which are not highest weights. And these POVMs are more complicated, and they are not covered. Even for the SU2, they are not covered by results of Lee Solovay. So the minimizers of this functional are unknown in general. And some colleagues have done numerics, and they saw that, for instance, it does not seem to be true that coherent states are always the minimizers. For some cases, they seem to be, and for some others, they were getting some other. So it's just open. So the leading asymptotic of the minimal output entropy of channels is related to this functional, but it is not known what are the optimizers or minimal values of this functional. And this, I think, I wanted to stop with. And thank you, and sorry for going so long.
Thank you, Błażej, for a great talk. We have time still, I think, some time for questions, comments. Marek?
If the rank of the group is larger than one, SED, for example, so Cartan algebraic, or dimension, say, d minus 1, okay? So then the highest way representation is characterized by more than one parameter. It was JSON, okay? So what could be this small parameter? 1 over j was here. What would be that?
Yes, thank you. So maybe maybe let me.
So in other ways, so representations are numbered by more parameters.
Yes, yes. So maybe in order to not be too abstract, I will discuss a little bit the case of SU3 that has 2 parameters, and we can draw on the whiteboard. So there are 2 Dynkin indices that label representations or highest weights. And so we have grid points in a quadrant of a plane. And the case where the phase space is a projective space corresponds to these lines where one of the coordinates is 0 and the other is going to infinity, and either horizontally or vertically in this case. All the other weights are the generic case, and generally speaking, I think in generic case you should one should take all the components to infinity, say in such a way that their ratios converge. So, for instance, one situation is that you take one fixed point in this diagram and you just rescale it by a factor n and go to infinity. So that's allowed. And
what would be the dimension of this phase space then? Because if I go on this line and on this line, I know it will be one 6-dimensional, one 4-dimensional. What would be that? Because
why do you say 6-dimensional?
No, this classical phase space, okay, it has some dimension. Okay?
Yes.
This is a manifold, okay.
So for SU3,
and if I go with this will be 6-dimensional, this 4-dimensional. It depends how you go.
Yes.
So what would be if you go?
So here it would be CP2, which is 4-dimensional. Here it would also be CP2, which is 4-dimensional. And for these limits going in the generic directions, it would be SU3 divided by the maximal torus. This maximal torus.
So it will be 4-dimensional.
Well, SU3 has 8-dimensional, and the torus is 2-dimensional. So 6-dimensional phase space. But in practice, what's sort of scary about these things is not so much.
I'm much interested in this Berezin transformation in this case. So this is what goes to this. For example, you have such a estimation which SU3 clearly explained, it is not so that it should be small. It could be not small, but nevertheless, formally it was small because it was divided by 2j plus 1. Okay, 2j plus 1 is in the sense this parameter. So it is interesting what would be here. So I had some experience with that. This kind of be different setting. That's why I'm asking in this language what does it mean. Okay.
So I mean the fact that there is this convergence of the resin transformations and there is an asymptotic expansion in terms of star products. This is known in general for these limits. There is a very general theory of quantizations of Kähler manifolds, the so-called Wehrl-Interpret's approach, and it applies here. So one has these general results, but in practice it seems that sort of methods which are tweaked to the problem, which use very strongly all the symmetry and representation theory, give much better results. And I don't think that these very optimal, for example, these very optimal results are known. Furthermore, for example, the star product that I displayed, my understanding is that in general, there are complicated diagrammatic expansions for subsequent terms, but there are no closed formulas for these things. So it's much more complicated. And in some sense, the curves or the problem with this is not so much the dimensionality of the manifold, but its number of sort of independent differential operators. So if we go to larger SUD,
yeah, I agree that in this case the dimensionality of this classical manifold could not play a role. But in our case, what we considered, especially for SU3, was because the dimensionality of this classical phase spaces was different exactly which kind of representation you choose. So the system could be the same, formally the same system quantum mechanically could be in classical limit, either integrable or non-integrable, because this depends on the dimensionality of the phase. So okay, but I understand. So, but I wanted to understand this in this language of this resin transformation. That's why I asked. I will send to the papers. Thank you.
Other questions or comments? Oliver?
I wanted to ask a little bit about the conjecture you mentioned in your last couple of slides, and it seemed like the impression I just got from your slide was that the numeric suggested that this conjecture was false in general, or
no, so because I was going a bit too fast because I was already over time. So the conjecture would be that this entropy and also other functionals corresponding to other anyhow maybe the entropy is minimized for coherent states, but this is only for the Cauchy function, which is defined in terms of the highest weight vectors, and this you can ask for other groups, and it's not known, doesn't seem to be known whether it's true. Now, in the statement here, we have a different generalization. We are still at the level of SU2, where the conjecture is known to be true, but we are using different weight vectors to define this sort of generalized Cauchy function. And this is basically clear that the conjecture does not extend to this regime. It's more complicated and different POVMs will have different optimizers. And so sort of my hope when I started working on this was that we would from this obtain an asymptotic expansion of the minimal output entropy for all these channels. But in fact, the functional that you get here, you don't have no idea how to minimize. And the funny thing is that the way Lieb and Solovay proved the conjecture for the highest weight case, they actually first proved a statement for channels and took a limit. So they really did a quantum computation and they derived the classical sort of counterpart by taking a limit, not the other way around.
Thank you.
And they proof will not work for this generalized Cauchy function.
Other questions, comments? I have maybe one technical about exactly this formula. So, did you analyze this entropy functional also for the case of SUD, where and like for different weight, like pushing like it, like let's say, is it true that those external channels also come, let's say, from like smearing of some measured and prepared channels on done on now weight vectors?
Yeah, so for the projective space case, it's also true that well, they also correspond to POVMs, but in general not rank 1 POVMs, because in the end, what's relevant is actually not what are the weight vectors, but you have this stability group K of the highest weight, and you take the representation and you decompose it into irreducible representations of K. In the case of the symmetric representations of SUD, you have this situation where, sort of in the bosonic language, right? Symmetric representations are related to bosons. We are distinguishing one type of boson, all bosons in the sort of first basis vectors, and there is a complement.
Sure.
And the extreme POVMs correspond to counting how many bosons are in the first vector and how many are in the others. So counting bosons in the distinguished direction and all the rest. And there are similar formulas, but I think Tommaso put them in his PhD thesis. We never published that actually. And the numerical simulations, I think that was done by Robin Roivers, not by myself. So I only had it from him. I think he did it for SU2, and he was telling me that you change this M and the minimizer changes. For some range, you still see to be getting coherent state, and in some other, he was getting some completely different state.
Nice. I have one more question, just maybe quick one. So you had this approximation of the operator via Belazian transform for SU2. Do you have analogous bounds for SUD as well for this symmetric bosonic representations?
Well, I'm not sure which bounds you are referring to. This, for instance, is because this is completely general.
No, I mean, like how you take operator that was from the other sort of direction. Next.
Maybe
this one, yeah.
No, so first of all, I mean, for the complex projective space, an analogous bound holds. Yes, so there would be 1 over n here, and this would be replaced by the Casimir. I don't think we have it published, but I think the same method of function. Well, no, we do have it actually. We do have it. Yeah. So there is a statement like this. There would be some numerical constant and 1 over n, where n is the sort of number of bosons or number of.
Sure. Okay, that's actually very interesting. And this P can be infinite as well.
This P can be infinite, yes.
Cool.
So it can even be other norms, because the way of proving this inequality is actually quite curious. So the left-hand side can be obtained from the left-hand side before taking the norm can be obtained from the right-hand side by an action of a certain positivity preserving transformation, and this positivity unital positivity preserving and trace preserving transformation, and these maps are contracted with respect to all shuttle norms and also for other norms. So if you can control the right hand side, then the left hand side can be controlled in almost any way. I mean, if you want to compute functions of operators or anything like that, I think you can do it.
Okay, nice. Sounds quite powerful. Okay, if there are no, it's actually very exciting. If there are no further questions, let's thank Błażej again.